Welcome to this problem walkthrough. Today, we'll explore problem number 741, cherry pickup. This is a fascinating dynamic programming problem that challenges us to find the maximum cherries we can collect while navigating a grid. We'll break down the problem, consider various approaches, and analyze the solution step by step. Let's get started. In this problem, we are dealing with a grid-based field where each cell is either empty, contains a cherry, or is blocked by a thorn. A cherry is represented by the value 1, an empty cell by 0, and a thorn by -1. You have two players starting at the top left corner of the grid, at cell 0, 0. Both players need to move simultaneously to the bottom right corner of the grid, at cell N1, N1. At each step, the players can only move either down or to the right. Once they reach the bottom right corner, both players return back to the top left corner. On their return journey, the players can only move up or to the left. Throughout both trips, the players collect cherries from the cells they visit. However, if both players happen to visit the same cell, only one of them can collect the cherry from that cell. The goal is to maximize the total number of cherries collected by both players by the end of their second trip. If it is impossible for either player to find a valid path to the destination, the result should be 0. The input to this problem is a 2D grid or matrix of integers, where each element is either -1, 0, or 1, representing thorns, empty cells, and cherries, respectively. The grid is always square, with dimensions n×n, where n is at least 2 and at most 50. The output is a single integer that represents the maximum number of cherries that can be collected by both players combined. If there is no valid path for either player to complete the journey, the output should simply be 0. Let's look at some examples to better understand the problem. In the first example, the grid is a 3x3 matrix. The first player starts at cell 0, 0, and follows the path 0, 1, 1, 1, 2, 1, 2, 2. Along this path, the player picks up cherries with values 1, 0, 1, and 1, for a total of 3 cherries. The second player begins their return journey from 2, 2, and moves backward along the path 2, 1, 1, 1, 0, 0. On this path, the second player picks up cherries with values 1 and 1, for a total of 2 cherries. Combining the cherries collected by both players, the total comes to 5. This is the maximum number of cherries that can be collected in this scenario. In the second example, the grid also has dimensions of 3x3. However, in this case, it is impossible for either player to complete the journey because the thorns block access to the bottom right corner of the grid. Since the players cannot find valid paths to their destinations, the output is 0. This highlights how the presence of thorns can completely prevent cherry collection if the paths are obstructed. In the third example, the grid is larger, with dimensions of 4x4. Here, both players are able to take optimal paths that maximize the total number of cherries collected. The first player collects cherries during their forward trip to the bottom right corner, while the second player collects cherries on their return trip to the top left corner. Together, they manage to collect a total of 12 cherries. This example illustrates how careful path selection can lead to significant cherry collection even in larger grids. To handle the constraints efficiently, an optimized dynamic programming approach is necessary, as the grid size and the player's movement options can create a vast number of possible paths. To solve the cherry pickup problem, one initial approach we can consider is the brute force method. The intuition here is to explore all possible paths through the grid to maximize the number of cherries collected. Starting at the top left corner of the grid, at position 0, 0, we attempt every valid path to the bottom right corner, at position N1, N1. Once there, we reverse direction and trace back to the top left corner, again attempting all possible paths while trying to collect additional cherries. This approach takes into account that some cherries can be collected twice, once on the way down and once on the way back. However, there are important constraints, such as avoiding blocked cells, which are represented by -1 in the grid. The major drawback of this approach is that the number of possible paths grows exponentially with the grid size, leading to a time complexity of O(2)(2n). This makes the brute force approach computationally infeasible for larger grids, as it becomes too slow to solve the problem in a reasonable amount of time. A more efficient way to approach this problem is by using dynamic programming with a 3D DP structure. Here, the key idea is to represent the problem as if two travelers are moving simultaneously from the top left corner to the bottom right corner, both sharing the same grid. We define the states as R1, C1, C2, where R1, C1 represents the position of the first traveler and R2, C2 represents the position of the second traveler. Since both travelers share the same grid, we ensure that they cannot pick the same cherry twice. Additionally, if either traveler steps on a blocked cell, the path becomes invalid. The state transition involves computing the maximum cherries that can be collected based on the previous states, while adding the cherries collected at the current positions of both travelers. This approach reduces redundant computations by building on previous results, and since the DP table size is O(n cubed, the overall time complexity is also O(n cubed. While this solution is much more efficient than brute force, its space complexity of O(n cubed can still be quite high for larger grids. To address the high memory usage of the 3D DP approach, we can optimize it further using a 2D DP structure. By observing that the second traveler's row, R2, is determined by R1, C1, and C2, we can eliminate the explicit storage of R2. This allows us to reduce the state space and maintain only two 2D arrays, one for the current row and one for the previous row. The transition logic remains largely the same as in the 3D DP approach, where we calculate the maximum cherries collected based on valid moves from previous states. This optimization reduces the space complexity from O(n cubed to O(n squared, making it much more practical for larger grids while still retaining the same time complexity of O(n cubed. Given these improvements, the 2D DP approach strikes a good balance between efficiency and memory usage and is well suited for solving this problem at scale. When comparing the different approaches, it's clear that each has its own trade-offs. The brute force method, with its exponential time complexity, is not practical for larger grids due to its inefficiency. The 3D DP approach significantly improves on this, providing a polynomial time solution with O(n cubed time complexity, but its high space complexity of O(n cubed can be a limitation. The 2D DP approach retains the same time complexity as the 3D DP method but optimizes space usage, reducing it to O(n squared. This makes it far more scalable and efficient for larger grids. Overall, the 2D DP approach offers the best balance of clarity, efficiency, and scalability, making it the ideal strategy for solving the cherry pickup problem effectively. The cherry pickup problem challenges us to optimize the collection of cherries from a grid while making two trips. Both trips start at the top left corner of the grid and end at the bottom right corner. Each traversal must adhere to specific movement rules, allowing only downward or rightward moves. Additionally, cherries picked during the first traversal cannot be picked again during the second. To solve this, a brute force approach initially attempts to enumerate all possible paths. Starting from the top left corner, we recursively explore every path to the bottom right corner, collecting cherries along the way. With two traversals allowed, this process is repeated for the second trip. However, we must ensure that the paths stay within the grid boundaries, and any path passing through a cell containing -1, which represents a thorn, is immediately invalidated. This forms the basis of the brute force method, though it is computationally expensive. Once all path combinations have been explored, the brute force approach returns the maximum cherries collected across the two traversals. However, this method suffers from significant inefficiencies. Recursively exploring all paths results in redundant computations due to overlapping subproblems, where the same path segments are recalculated multiple times. Furthermore, the number of possible paths grows exponentially with the grid size, leading to an infeasible O(2)(2n) time complexity for larger grids. To address these limitations, we turn to dynamic programming. By storing the results of overlapping subproblems, we avoid redundant calculations and drastically improve efficiency. The first step in this optimized approach is to define the state variables. Here, we use a function dp, x1, y1 and x2, y2, which represents the maximum cherries collected when the first traversal is at position x1, y1, and the second traversal is at position x2, y2. This structured approach lays the foundation for our dynamic programming solution. To implement the dynamic programming solution, we start by defining the base cases. If either traversal moves out of bounds or encounters a thorn, a cell with value -1, the result for that state is set to -infinity, indicating an invalid path. If both traversals successfully reach the bottom right corner, the cherries at that cell are returned. Next, we define the transition logic. For any state dp, x1, y1 is x2, y2, we calculate the maximum cherries by considering all valid previous states. The first traversal could have arrived from either the cell above or the cell to the left, while the second traversal has similar options. For each combination of previous states, we add the cherries collected at the current positions of both traversals, taking care not to double count if both are at the same cell. To reduce the complexity further, we observe that x2 can be expressed in terms of x1, y1, and y2 due to the constraint x1 plus y1 equals x2 plus y2. This allows us to simplify the state representation to dp, x1, y1, y2, reducing the dimensionality of our dp table to 3. Analyzing the optimized solution, we find that its time complexity is O(n cubed). This is because we calculate dp, x1, y1, y2, for all valid states, and each state requires a constant number of transitions. The space complexity is also O(n cubed), as we store intermediate results in a 3D dp table. Edge cases must also be considered. For instance, if the grid is filled entirely with thorns, the algorithm should correctly handle the absence of valid paths. If the grid contains just one cell, the result is the value of that single cell, provided it is not a thorn. For larger grids, such as n equals 100, the algorithm's performance should be validated to ensure it remains efficient and practical. These considerations ensure that the solution is robust and capable of handling a wide variety of grid configurations. To see the algorithm in action, let's walk through an example. Consider an input grid like this: 0, 1, -1, 1, 0, -1, 1, 1, 1. We begin by initializing dp 0, 0, 0 to the value of the starting cell, which is 0. Using the dp transition formula, we expand states step by step, accounting for all valid paths and ensuring no double counting of cherries. After calculating all entries in the dp table, the final result is found at dp n1, 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 which represents the maximum cherries collected across both traversals. For this grid, the maximum cherries collected is 5. This example demonstrates how the dynamic programming approach efficiently computes the result while handling the constraints of the problem. Here, we start by defining our solution class and implementing the cherry pickup function. The goal is to use dynamic programming to calculate the maximum number of cherries two people can collect starting from the top left corner of the grid and ending at the bottom right corner. First, we determine the size of the grid, n, and initialize a 3D dp table, dp, with dimensions nx and xn. Each cell in this table represents the maximum cherries collected when one person is at x1, y1, and the other is at x2, y2. The table is initially filled with negative infinity to signify unvisited or invalid states, except for the starting cell dp 0, 0, 0, which is set to grid 0, 0, representing the cherries at the starting position. Next, we iterate through all possible positions of x1 and y1 for the first person, and x2 for the second person. The corresponding y2 position is calculated as x1 plus y1 x2, ensuring both paths remain valid. If any position is out of bounds, or if either person lands on a thorn, indicated by -1 in the grid, we skip that iteration. Otherwise, we check all possible ways to transition into the current state, such as moving from the left or above for both persons, and update the dp table with the maximum cherries collected so far. Finally, we add the cherries at the current positions of both persons to the dp value, taking care to avoid double counting when both persons are on the same cell. The function concludes by returning the result stored in dp n1, 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 which represents the maximum cherries collected when both persons reach the bottom right corner of the grid. Since it's possible that no valid path exists, we use max 0 to ensure that the result is non-negative. This guarantees that the function returns 0 if no cherries can be collected. With this implementation, we've successfully used dynamic programming to solve the problem of maximizing cherry collection while ensuring both individuals follow valid paths. Here, we begin by importing the necessary classes and defining our solution class. Inside it, we implement the cherry pickup method, which takes a 2D grid as input. The first step is to determine the size of the grid, n, and then initialize a 3D dynamic programming array, dp, of dimensions nx and xn. Each element in this array will represent the maximum cherries that can be collected when two players traverse the grid from the top left corner to their respective positions. Initially, we fill all elements of this DP array with integer.min_value to signify uncalculated or invalid states, ensuring we can later compute maximum values effectively. The base case is set by initializing dp 0, 0, 0 to grid 0, 0, as this is the starting point where both players begin. Now, we iterate through all possible positions for the two players using three nested loops, x1, y1, and x2, where y2 is derived as x1 plus y1 x2. This relationship ensures that the total number of steps taken by both players remains synchronized. If y2 goes out of bounds, or if either player lands on a cell with -1, representing a thorn, we skip that state. Additionally, we update dp x1, y1 is x2 by considering the maximum value achievable from the previous step of each player. For instance, if player 1 moves from the left, the value is updated using dp x11, y1, x2. Similarly, we handle other movements like coming from the top for player 1 or player 2 moving from their respective previous states. These transitions ensure we accumulate the best possible cherry count up to this step. Next, we continue the update process by handling additional transitions. For example, if player 1 moves from above, we update the dp x1, y1 x2 value using dp x1, y1 1, x2. Similarly, transitions for player 2 are managed, such as moving from the left or above. This ensures that all possible paths for both players are accounted for. After computing the maximum value at a given state, we add the cherries collected at the current positions of both players. Specifically, grid x1, y1 is added to dp x1, y1, x2. If both players are not at the same position, we also add grid x2, y2 to avoid double counting cherries. This step ensures that we are accurately accumulating the cherries collected while both players traverse the grid. Finally, the method returns the maximum cherries collected when both players reach the bottom right corner of the grid, which is stored in dp n1, n1, n1. If no valid path is possible, we return 0 by taking the maximum of this value in 0. This approach ensures that the result is always non-negative, as collecting no cherries is preferable to an invalid result. The implementation effectively uses dynamic programming to solve this problem by breaking it into smaller subproblems and ensuring all possible paths and transitions are covered. Here, we're starting with an example grid that has no obstacles. The grid is a 3x3 matrix where 1 represents a cherry, -1 represents an obstacle, and 0 represents an empty cell. The goal is to maximize the cherries collected while moving from the top left to the bottom right corner and back. To solve this, we first initialize a 3D dynamic programming table dp with dimensions nx and xn to represent the state of two paths simultaneously. Each state, x1, y1 x2, corresponds to two positions, x1, y1, for one path and x2, y2, for the other, where y2 is derived as x1 plus y1 x2. Initially, all values in dp are set to INF to signify invalid states, except for the starting position dp 0, 0, 0, which is initialized to the value of grid 0, 0, which is 0 in this example. This sets up the foundation for calculating the optimal paths through the grid. Now, we iterate through all possible valid states, x1, y1, x2, in the dp table. For each state, we calculate y2 equals x1 plus y1 x2 to determine the position of the second path. If y2 is out of bounds or if either x1, y1, or x2, y2 lands on an obstacle, we skip that state. For valid states, we update the dp value by considering the maximum cherries collected from all possible previous states. These transitions represent moving either path from the left or the top, and we add the cherries at x1, y1, and x2, y2. If the two positions are the same, we only add the cherries once. By carefully updating dp through valid transitions, we ensure that we account for the maximum cherries that can be collected up to that state. For this example, the final result in dp, n1, 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 is 5, representing the maximum cherries collected with no obstacles in the grid. Next, we analyze a grid that includes obstacles. The initialization process remains the same. We set up the dp table with INF values and initialize dp 0, 0, 0 with the value of the first cell, which is 1. As we iterate through valid states, we encounter situations where obstacles block certain positions. For instance, at x1 equals 1, y1 equals 1, x2 equals 1, the calculated y2 is 1, but grid 1, 1 contains -1, so this state is skipped. For other valid states, like x1 equals 2, y1 equals 2, x2 equals 2, where no obstacles are present, we calculate the transition values. For example, dp 2, 2, 2 is updated by taking the previous maximum value and adding the cherries at 2, 2. Here, the result is 5 because the optimal paths avoid obstacles while collecting the maximum cherries. This example demonstrates how the presence of obstacles introduces constraints that dynamically shape the valid paths in our solution. In our final example, the grid is completely blocked, meaning no valid paths exist from the start to the end. The initialization process begins as usual, with dp 0, 0, 0 set to the value of the first cell, which is 1. However, as we iterate through states, we find that all potential paths are invalid due to obstacles. For instance, at x1 equals 1, y1 equals 0, x2 equals 0, the calculated y2 is 1, but grid 1, 0 contains -1, so this state is skipped. Similarly, there are no transitions that lead to the bottom right corner. As a result, the dp value for the final state dp n1, n1, n1 remains inf, and the output of the function is max 0 dp n1, 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 which ensures a non-negative result. In this case, the output is 0, reflecting that it's impossible to collect any cherries. This highlights the importance of handling edge cases like full blockages in the grid. This solution employs a dynamic programming approach using a 3D dp table, dp, x1, y1, x2. Here, x1 and y1 represent the coordinates of the first person, while x2 represents the x-coordinate of the second person. The y-coordinate of the second person, y2, is derived from the relationship y2 equals x1 plus y1 x2. To evaluate the time complexity, we first consider the outer loops. The algorithm iterates through all possible values of x1, y1, and x2, each ranging from 0 to n1, leading to 3 nested loops and a total of n³ iterations. Within each iteration, the inner work includes steps such as validating the derived y2 coordinate to ensure it is within bounds and processing up to 4 possible transitions to determine the maximum cherries collectible for the current state. Since each transition involves constant time operations, such as checking and updating values, the inner work is O(1). Combining these, the overall time complexity of the algorithm is n³. Now, let's analyze the space complexity. The primary contributor to space usage is the 3D dp table, which has dimensions nx nxn corresponding to the possible values of x1, y1, and x2. This results in a space requirement of n³. Apart from the dp table, the algorithm uses additional space for loop variables and intermediate calculations, but this is minimal and classified as O(1). Therefore, the total space complexity is dominated by the dp table, making it n³. Additionally, the time complexity remains n³ across all cases best, average, and worst, because the number of iterations is fixed by the grid size. Similarly, the space complexity of n³ is constant in all cases, as the size of the dp table does not depend on the grid's specific configuration. To put this into perspective, let's compare this dynamic programming approach to a brute force solution. In a naive method, both individuals would explore all possible paths independently, summing their cherry counts. Since each person can take up to 2n steps, with 2 choices per step, the total number of paths for one person is 2n. For 2 people, this balloons to 2 for n, which is computationally infeasible for larger grids. By contrast, the dynamic programming solution drastically reduces this exponential search space to a polynomial 1. By leveraging overlapping subproblems and considering only valid states, the time complexity is reduced to n³. Mathematically, this is achieved because the 3 nested loops, iterating over x1, y1, and x2, directly contribute n³, and the constant time operations within the loops do not add any additional factors. For space, the 3D dp table, which stores values for all possible states, x1, y1 is x2, results in n³ memory usage. No extra recursion stack or auxiliary data structures are needed, ensuring the space complexity remains efficient and manageable. When solving the cherry pickup problem, there are a few common mistakes that can trip you up. First, ignoring constraints like the grid size or specific movement rules, such as only allowing movement to the right or down, can lead to incorrect assumptions about the problem space. This can result in inefficient solutions that fail to scale or paths that violate the movement rules entirely. Next, failing to handle edge cases is another pitfall. For instance, think about grids with no cherries, grids filled entirely with obstacles, or paths that require backtracking. These scenarios can easily be overlooked and cause your solution to fail. Another critical mistake is not accounting for overlapping subproblems in dynamic programming. If intermediate results aren't memoized, you'll end up recalculating the same states multiple times, which can blow up the time complexity from something manageable like n squared or n cubed to exponential growth, making your solution impractical for larger grids. Another mistake to watch for is mishandling base cases in recursion. For example, base cases like out-of-bound indices or cherry collection conditions must be handled carefully. If you fail to return 0 for invalid coordinates or neglect to define what happens when you reach the bottom right corner, your solution might produce incorrect results. Additionally, hard-coding path constraints is a subtle but significant issue. If you restrict your solution to specific movement directions, such as only right and down, you make your code inflexible. This becomes problematic when the problem introduces variations, such as diagonal moves, and increases the debugging complexity when adapting your solution. Ensuring flexibility in your approach is key to handling these variations smoothly. Now, let's consider some insights that are particularly useful for interviews. One of the first things to do is to look for patterns. Cherry pickup often involves dynamic programming on a 2D grid, so recognizing that paths from the top left to the bottom right can overlap is crucial. By leveraging memoization, you can avoid redundant calculations and optimize your solution. It's also important to think in terms of states. Clearly define what each state represents. For example, in a DP approach, a state could represent a position in the grid and the number of cherries collected so far. Be mindful of trade-offs as well. While brute force guarantees correctness, it's computationally expensive and impractical for large grids. A DP approach, on the other hand, trades memory for performance, making it far more efficient. During interviews, make sure to explain how your solution handles edge cases, as this is a common area where candidates struggle to demonstrate full understanding. For additional practice, related problems like minimum path sum, unique paths, and unique paths 3 can help reinforce these concepts. Finally, let's explore some alternative approaches you might consider. The first is brute force, where you recursively explore all possible paths. This approach is simple to implement but comes with a major drawback: its exponential time complexity makes it infeasible for larger grids. A more practical solution is dynamic programming, where you use a 2D or even 3D DP table to store the maximum number of cherries collected at each state. This method is highly efficient for medium to large grids, but it requires careful state management and can be tricky to debug. Another approach is greedy, where you attempt to maximize the cherries collected at each step locally. While this method is fast, it's often unsuitable for global optimization problems like cherry pickup, as it can lead to suboptimal results. Choosing the right approach depends on the specific problem constraints and the size of the grid you're working with. Great job! We've just completed problem number 741, cherry pickup. We reviewed the brute force approach and discussed how dynamic programming helps optimize path-based problems. Remember to practice similar problems to strengthen your problem-solving skills. Thanks for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!